All right, let's see how well you did on this opening problem here. Practice simplify. So there's no I in the denominator. This is 17-1, day number 2. We always, if we want to get rid of an imaginary number in the denominator, we multiply by what's called the conjugate. Okay, whenever you get an I squared, think -1. Okay, so in this case, in the numerator, I'm going to have to FOIL, but in the denominator, I only have to Florida, right? Because of those conjugates. So old people love conjugates. In the numerator, what do we get? Well, we get 6 plus 3i plus 2i plus I squared. All right, let's simplify that right quick here. I get 6. What is I squared again? -1. So I get a 5 plus a 5i. Comfortable? Okay, now I Florida in the denominator here, which is 2 times 2, which we know is 4. And -I times I, which is -I squared, which is -1, which is a positive 1. So 4 plus 1 is 5. So this number in a plus bi form is 5 over 5 plus 5i over 5, which we could then rewrite. Oh, see how I use that? That's cool. 1 plus I. There we go. There's our imaginary, our complex number in a plus bi form. Let's continue with our lesson, children. Okay, here are some practice problems. I'd like you to take the next, let's go 5 minutes. I'm requiring you have to do A, you have to do B, and you have to do F. A, B, and F. I'll cover the answers for the others as well, but A, B, and F are required. Go. Talk with the neighbor. All right, so part A, I'm going to take each of the components, the real components, add them. So that's square root of 2 plus square root of 2, which is 2 of those. If you wanted to write square root of 8, you could. That'd be varsity. The second component, which is the imaginary portion, is going to cancel when I add those. So this is my answer. Chill. 2EC. Okay, in part B, I'm going to take 1 over z. Well, z is this. That means I'm going to want to get rid of the imaginary portion in the denominator. So I multiply by its conjugate. If I multiply by its conjugate, bottom and top, that's root 2 plus I root 2. Root 2 plus I root 2. So we're going to Florida the bottom. What will we get? What's root 2 times root 2? 2. And what is I times I? I squared, which is -1. But I've got a negative here, so it'll be a positive 1. And root 2 times root 2 is 2. So I've got 2 plus 2, which is 4. So the denominator comes out to be 4. In the numerator, I have one of those. And there's our answer for B. All right, for the last one, part F here. Oh, sad. Okay. What is this, that line over that mean? Conjugate, right? So this is z times its conjugate. Well, z is root 2 minus I root 2. We actually just did this. And root 2 plus I root 2. We said that was 4, right? That is z times its conjugate. Now, for those who need it, I'm going to do this because maybe, you know, you're trying to watch Gilmore Girls and do this at the same time, which is just, you know, I could understand if it was Hawaii 5-0 action-packed. You know, you're just like, dang. Marky Mark and the Wahlburgers. So I'm going to do first root 2 times root 2, or root 2 squared, that's 2. Yeah, if you're watching Marky Mark right now, just shut this off right now and enjoy the awesomeness of him. Okay, and then negative I times I is negative I squared times root 2 times root 2, which is root 2 squared. I squared is negative 1, but that negative will negate it, so I'll get 1 times square root of 2 squared, which is 2. So that gets 2. So then I add those two items together, right? And so I get that z times its conjugate will equal 4. Okay, here we go. I am going to explain all this math blah in picture form. How many of you are visual learners? I'm going to show it to you in picture form. You ready? An imaginary solution to, let's say, a quadratic like this. Can you factor that? If you can, you're factoring on the complex plane. But this has two imaginary solutions. If you did quadratic formula, you'd find two imaginary solutions. And the reason why is because of this. Okay, first of all, there's going to be two solutions. So this function right here, this polynomial, that's going to have how many solutions? 3. Now, 3 possible or 3 total solutions. Now, could they all be real solutions? Could they? These here. Potentially. Sure, right? There's your polynomial. Actually, I drew that wrong, but it's okay. But it could have 3 real solutions. Is it possible that it has no real solutions? A cubic. Oops. Is it possible for me to draw a cubic that has no real solutions? Not possible, right? Because the end behavior tells me at least once it has to cross the x-axis. Okay, so an odd polynomial has to have at least one real solution. Now, the rest of the solutions could be imaginary. And the cool thing about it is that imaginary solutions always come in pairs. Conjugate pairs. Oh, old people love solutions, complex solutions. Now here are your options. You could have 2 real solutions, or you could have 2 imaginary solutions. But you can't have one of each. Is it possible to have only one real solution? Yeah, it is. That graph would look like this. But in actuality, it has 2 real solutions. They just both happen at the same place. Right? Because remember multiplicity? Multiplicity 2. Right? So if I drew you this, let's say I had x to the 5th plus, I don't know, x to the 4th minus pig nose x to the 3rd plus 11. It doesn't matter what those coefficients are. I'm just talking about graphically, what's the most imaginary solutions this could have? They come in pairs. So 4, right? What would that look like? If it had 4 imaginary solutions, what would it look like this? Right? Here's your real solution. The imaginary ones are just poof out there. We don't know. Right? What if I had x to the 6th plus real tall, skinny Dracula heart x to the 2nd minus 13? Could that have no complex solutions? Is it possible for that to have no imaginary solutions? Yes. Is it possible for that to have only 5 real solutions? No, because then that would mean that there's only one complex solution, which we know doesn't happen because they come in pairs. That make sense? Correct. So for example, let's go back up to the example I just had up here. X squared, let's go with something a little bit easier, plus 9. Okay, that's a parabola, right? That's been shifted upward how many units? 9, right? So it's going to have no real solutions, never going to cross the x-axis. So let's use quadratic formula here for a moment to find out what those solutions would be. And you'll see that they're conjugates. Okay, so x equals negative b, well, b is 0, plus or minus square root b squared, which is 0, minus 4 times a times c all over 2a. All right, so the 0 is just going to go away. I'm going to have plus or minus the square root of negative 36 over, oh, that should be a 1, over 2. Well, that's going to equal plus or minus 6i over 2. So x will equal plus or minus 3i. So how would I factor that? Well, x squared plus 9 in factored form is x plus 3i, x minus 3i. That's in factored form. So far, so good? Okay. We're going to do a little bit of synthetic division with some nastiness involved. Okay, you ready? We're going to do synthetic division with imaginaries. So, first of all, here's the deal. If I know that this is a 0 of f, right? And I'm calling f this, x to the 4th plus 64. If I know that is a 0, what else is another 0? Correct. Okay, so I already know 2 of the zeros. I'm going to find the other 2, but first, it looks like part 1 wants me to use synthetic division to show that that is a 0 of f. So how I'm going to do that is x to the 4th plus 0x to the 3rd plus 0x squared plus 0x plus 64. That's my polynomial. And into that, I want to divide this 0. I'm going to use synthetic division because I like it better. Long division is going to get ugly. All right, I could put into there x minus 2 plus 2i. I don't know. How do you guys feel about doing that long division? Let's not. Let's use synthetic. Okay, so what do we do with synthetic? We take all of the coefficients. I got a 1, a 0, a 0, a 0, and a 64. If it's true that this right here, 2 plus 2i, is a 0 of this polynomial, when I get to the very end, what should I get? Yeah, I should get a remainder of 0. All right, so we take the fundamentals of this process, and we drop down the first number. And then what do I do at 2 plus 2i and 1? Multiply. So 1 times anything is that anything. And then instead of subtracting like we do with long division, we're going to add. So I get 2 plus 2i. Okay, now I have to multiply. So I'm going to do 2 plus 2i times 2 plus 2i. Let's do that off to the side here real quick. Foiling, I get 4 plus 4i plus 4i plus 4i squared. Let's simplify that. I know that's 8i. 4i squared is what? Negative 4. So 4 and negative 4, they cancel. So I get 8i. Okay, 0 plus 8i is 8i. And now I multiply again. 2 plus 2i times 8i. Well, this will be a lot easier. That'll be 16i. And then plus 16i squared. What's that going to be? 16i minus 16. Okay, so I got a 16i minus 16. Now I'm going to add those. I get 16i minus 16. And I got to multiply one more time. So I got 2 plus 2i times 16i minus 16. So I get 32i minus 32 plus 32i squared minus 32i. Oh, this is going to be great. What happens to my 32i's? They're gone. I get negative 32 minus 32, right? Because that's an I squared. So I get negative 64. Shown. Watch this. I have proven, since the remainder equals 0, that that is a 0 of the polynomial. 0. We just did it. right? We showed that it's a 0 right there. Now what I'm going to do, and you're going to say, oh, no, it's not a big deal. I'm going to do it again with the other 0 that we had determined. Now with our new coefficients. Okay, our new coefficients being these right here. And you'll see why in just a minute. So I'm going to take 1, 2 plus 2i, 8i, and 16i minus 16. Because if that is a 0 right here, 2 minus 2i, what's true about the remainder there? Should also be 0. So let's see. Let's make sure it works. And it should, seeing that I did this about 20 minutes ago. So help me not screw it up. I drop down the 1. I multiply by 2 minus 2i. Well, that's going to be 2 minus 2i. What's going to happen here? I get 4. Oh, okay. I get 4. Then I multiply 2 minus 2i times that. So I get 8 minus 8i. Oh, I'm liking what I'm seeing. What happens to the 8i's? They're gone. Now I multiply again. That's going to be 16 minus 16i. What happens to these two? They gone. What happens to these two? They're gone. So I get 0. So what does this mean then? What is this? That's the remainder. Or that's the rest of the polynomial that's left. So let me go back up to the original piece of the problem here, the original setup. Look at these two polynomials, right? They're both quadratics, which means if I multiply them together, I'd get a what we call a quartic. Holy smokes, look at that. So that's what I have left. So this polynomial right here, the two solutions of that polynomial are 2 plus 2i and 2 minus 2i. If you factored and found the zeros, that's what you would get out. So let's write this down at the very bottom. What is it? X squared minus 4x plus 8. That would yield for me that right there. Okay, that's what we just found. Now in this case, we're going to see whether or not the other piece involved has real solutions or not. Is this blue one factorable? Two numbers that multiply to 8 and add to 4? No. Doesn't work. So I have to use quadratic formula. Let's do it quick. X equals negative b plus or minus square root. What's 4 squared? 16 minus 4 times a times c all over 2a. 2a is 1. I don't know why I keep putting a there. Negative 4 plus or minus, what's that going to be? Negative 16 all over 2. Well, if my calculations are right, I'll get this. What's that going to be? 2i. So the blue one will yield the following. How many real solutions are there for this polynomial? How many of those factors have only real numbers in them? Only real numbers. None. So this polynomial, it's a, let's look at what x squared, or x to the 4th plus 64 would look like. Would that ever cross the x-axis? No. Now, it might have a couple extra wiggles in there that we're not aware of, but it'll never cross the x-axis. Therefore, this right here, we have factored this over the complex plane. It has been factored over the complex plane. So we factored it over the complex plane, and we also know each of the zeros. Here are our zeros. And that is our factored form as well. Let's move on to the next page. Okay, so I'm going to give you a few hints, and I want the lowest degree polynomial that will meet each of these criteria. The graph y equals p of x touches but doesn't cross x at this point, right? At this point, which we'll call 1/3, comma 0. So if that's a 0, could I write out something, right? Some factor for that. If x equals 1/3 is a 0, could I write out a factor for that? Sure. What I would do is this. I'd multiply by 3 and then subtract 1. You agree? So that would be a factor of this polynomial. I'm going to write that out like this. I know this has to be a factor, right? We also know, given up here, that x equals 3i is a 0. Therefore, if that's true, one of these factors would be x minus 3i. What would the other factor be that pairs up with that? Yeah, x plus 3i. Okay. We know that those two would have to be factors because they come in conjugate pairs. Okay, now let's look at the end behavior. It says that as x goes to negative infinity, the graph goes down. And as x goes to the right, it also goes down. So what does that tell you about the degree of the polynomial? Is it even or odd? Even. And it's going to do what at 1/3? It's going to touch but not cross. So it's going to bounce off there. So it's going to bounce off there. Let's just say it looks like that. All right, let's write the minimum degree polynomial that would work for that. So what would the minimum possible degree have to be? Not x to the second, right? It has to be x to the fourth, right? Because if it's going to bounce off here, that's got to be 3x minus 1 squared, right, if it bounces. And if it has these values for other factors, then there's the other two, right? 1 and 1. So that's got to be a fourth degree. There's one thing we'd be missing. What is it? What is it? What's the end behavior? Down and down. So what does the leading coefficient have to be? Negative. So we'd toss a negative out in front. Okay? And it really doesn't matter. We could put a -10 out there, a -4, a -15, a -1/9. It doesn't matter. It just has to have the correct end behavior. Now, of course, we could change this, right? We could change this value to any even number, but then it just increases the degree of the polynomial. But we'd like to keep it at its simplest, and that's what we'd do.